optical networking for data center interconnect in an open SDN environment. I am John Mitchell, Director of Product Management at Sorrento Networks, part of the Contact Group. Cloud computing has started a revolution in computing. This is a quote from a recent report written by James Titcomb and published in Daily Telegraph Business, evaluating the impact of three tech titans, Google, Amazon, and Microsoft, on the emergence of the cloud. Traditionally, these have been leaders in the search engine domain, online retailing, and computer operating systems and application software. Now there is a new battle to define a new revolution that could become even more lucrative than today's construct. The revolution in computing started by the cloud. The cloud unfolds a new paradigm, a new way of doing and thinking about things. Instead of buying expensive compute servers, memory and storage, companies and individuals can rent online resources and services as needed by tapping into centralized data centers, not only saving on huge capital expenditure, but also negating the ongoing operation costs of staffed skills and complex maintenance contracts. The cloud is the big differentiator, for example, between listening to music stored on your own device and finding any song ever released from an online service such as Spotify, or losing an important document and having it permanently available from an online folder. The world is now accessing cloud-based services at an exponential rate. Netflix, which runs on Amazon's cloud platform, can make up a third of all internet traffic in the US at peak times. Snapchat, now only 5 years old, shows 7 billion videos a day running on Google's cloud. None of these services could run effectively and efficiently without the cloud and the online infrastructure of data center and optical networks which interconnect them and us to them. We have referenced Amazon, Google, and Microsoft, but we know there are many other cloud providers who have and will find profitable business models for their target markets. James Titcomb concluded his article with this telling phrase: "The cloud wars have just beginning." So, if we are just at the start, what do we need to maximize optical networking for data center interconnect, one of the foundational pillars of cloud infrastructure? A data center, the hub of the cloud, is not an island. Rather, it is an interconnect point between end users and other data centers. The interconnecting protocols of Ethernet and fibre channel have to be transported over physical media, sometimes called layer 0. For short reaches between equipment racks and aisles, copper interconnect is used. For longer distance, especially at higher data rates such as 1 gigabit, 10 gigabit and above, optical fibre is required. Multi-mode fibre is suitable for intra-building, can connect up to hundreds of meters in length. For inter-building or across metropolitan, national or international geographies, single-mode fibre is required, which can support optical transport over thousands of meters or kilometers. The graphic shows bundles of optical fibre in a single cable form which may be laid in a duct or directly buried. Cable forms may contain up to 144 or more individual fibres. Now that the layer 0 physical is in place, the optical layer 1 has to be added, which optically transmits the client traffic over the fibre optic line. Client signals from data networking or storage switches have short reach interfaces. The optical transponders, shown by the orange triangles in the graphic, transform the client signals from a short reach signal to an optical signal which can be transmitted over single mode fibre with a high laser launch power. There are two enemies which inhibit reach. Firstly, attenuation loss, which diminishes signal amplitude in the x-axis, whereby the receiver can no longer differentiate a digital 1 or 0. Optical amplifiers may be deployed in line to provide a power boost to increase reach. There is a limit to the number of amplifiers that can be used in any given span. Amplification also amplifies noise until the system hits OSNR, optical signal to noise ratio, whereby it can no longer operate error-free. Traditionally, the second enemy is distortion, either chromatic or polarization mode. Distortion tends to flatten the optical signal in the y-axis, also reaching a point where the receiver can detect data with errors. Traditionally, dispersion compensation modules are added along the span, which provide an inverse function of dispersion, squaring the optical pulses up again. However, dispersion compensation modules have inherent attenuation, and additional amplifiers are needed to be deployed to overcome the additional loss. Of course, dispersion compensating modules and optical amplifiers cannot be added infinitum due to OSNR system limits. Optical fibre is a costly resource to buy and to lay in the ground. Once deployed, it is imperative to maximize the data capacity that can be transported per fibre strand before implementing an expensive project of laying or renting more fibre. Increasing line rate is an effective solution whereby the means of electrical multiplexing, multiple lower rate signals can be mapped to a single higher rate signal, such as 10 by 1 gigabit data rates to a 1 by 10 gigabit data rate, making one fibre effectively do the work of 10 fibres. There are a number of electrical multiplexing schemes. Ethernet switching at layer 2 or OTN switching, which is 100% deterministic and guarantees zero data loss. Bandwidth capacity per fibre can be further increased by multiplexing additional channels in the optical domain. With each transponder transmitting a different wavelength of light, multiple wavelengths can reside on the same fibre. The number of channels that can be supported per fibre is a factor of spectral width and the spacing between the wavelengths. Typically, a 100 GHz spacing supports 40 channels, and the narrower 50 GHz spacing supports up to 88 channels per fibre. So, for example, with 100 gigabit line rate, channels up to 8 terabits per second can be transported per fibre, helping to support exponential growth in internet traffic. 100 gigabit transmission and above has additional complexities. As line rates increase, attenuation also increases. So where 10 gig on-off keying signal may travel 80 kilometers, a 100 gig on-off keyed signal can only travel 4 kilometers before errors arise. New, more efficient modulation schemes are needed for transmission of 100 gig and above signals. One such modulation scheme is DP-QPSK, dual polarization quadrature phase shift keying. Rather than just transmitting and detecting on-off pulses of light, phase modulation is used on two polarized planes, enabling 4 bits of data to be modulated onto a 25 gig carrier signal, equating to 100 gig effective data rate. One additional benefit of coherent detection is the opportunity for dispersion to be automatically compensated for, so that dispersion compensating modules and associated additional optical amplification is no longer required. Further modulation modes such as 8 QAM, quadrature amplitude modulation, and 16 QAM can increase symbol rate further, enabling 150 gig and 200 gig line rate transmission, deployable at the expense of reach. The graphic also shows an additional scheme which increases capacity further, superchannels, where 2 or more wavelengths are appended side by side to create a 300 or 400 gig transmission. Superchannels are a group of channels or subcarriers transmitted along the same path end to end and sharing a common spectral window. In this example, there are 5 subcarriers in the superchannel. FlexGrid further enhances the flexibility and deployment of superchannels. FlexGrid specifies a closer stacking of channels, 37.5 GHz spacing, and 6.25 GHz guard bands between superchannels. This further enhances spectral efficiency by up to 30% for fibre. Fixed spectral grids allocate transmission rates regardless of bandwidth needs. Flexible spectral grids supported by colorless transponder tunability enable efficient spectral use, delivery of 400 gig and 1 terabit capacity, and paves the way for adaptive line rates based on line conditions. Now that we have solutions for both reach and bandwidth capacity for fibre, focus moves to directing signals to where they need to go. Not all data center interconnect traffic is based on point-to-point fibre topology. Data centers and end-user connections may be built on a ring or mesh of interconnected fibers. Such topologies raise complexity when it comes to providing protection schemes in the event of a fibre break or intermediate line site outages. Having flexible add and drop and photonic switch elements in the network are now vital components. Optical add-drop multiplexers enable wavelength channels to be added or dropped at intermediate sites. The objective to have OADM are fully and remotely switchable without the need to manually swap optical patch cables from equipment to equipment. In this case, the additional remote optical add-drop mux element enables directionless networking between 3 sites. In a fully meshed fiber network where all the wavelength channels have to be available to avoid any channel contention, a remote optical add-drop multiplexer may be deployed as a collector and multiplexer for each degree of the site connectivity. Beyond layer 0 and layer 1, optical transport of getting data from A to B, there is an increasing threat of security breach on the physical fiber by externally tapping the fiber in an external connection or splice enclosure or even within the building. To maximize fiber security, transponders and muxponders are currently being offered with integrated encryption engines. This hard encryption with key exchange occurs at native line rate, so traffic latency is kept to a minimum and 100% of the traffic is secured, not just part of the payload as occurs in layer 2 or layer 3 encryption. Maximizing optical transport bandwidth per rack unit space is a big driver within data centers, where each rack unit has a space cost. Silicon chip geometries continue to scale down, meanwhile optical component integration is reducing transceiver real estate. State-of-the-art optical transmission systems supporting data throughput of 1 terabit per second are now being offered in a 2 rack unit chassis. This is something unimagined even a few years ago. 2 pressing issues remain data centers are space and power. Technology advancement also has seen significant drop in power consumption per gigabit of transmitted bandwidth, where now 10 gig of traffic can be transported, 100 gig of traffic can be transported by a transponder consuming just over 60 watts of power. The cumulative effect of such savings across a whole data center's worth of traffic is huge. Bringing all the elements discussed together, we see a network architecture which combines software programmable clients, optical transmission and switching, colorless, directionless, contentionless remote optical add-drop multiplexers, and spectral efficiency to provide flexible, lowest cost bit optical networking across any mix and range of topologies and geographies. On this graphic, we can see the client traffic, packet optical, storage, video, or traditional TDM, transponder and muxponder function, the multiplexer, demultiplexer couplers, and fixed or remote optical add-drop multiplexers, a mesh network, and the far end data centers or internet exchange points, a range of different fiber topologies, point-to-point, hub, ring, mesh, and the varying distances of access, metro, national, or long haul. Any end-to-end network requires a management solution whereby demands can be met in real time. Fast turn of service, with allocation and deallocation on demand, schedule services, and where full and clear performance measures can be reported readily to notify service level agreement compliance. For the operator, rapid fault management and alarm analysis are paramount. Also, network analytics, where network bandwidth bottlenecks can be identified dynamically and preemptive actions taken. Multi-vendor is a growing dynamic across the network, both within and external to the data center. Optical networking solutions must have open management interfaces to unlock the potential of SDN and enable a true applications level to operate at a vendor-agnostic equipment level. To conclude, James Kipton stated, "The cloud wars are just beginning. It will be a fascinating spectacle, but with a salutary note. Let us all make the right decisions regarding the fundamental foundational infrastructure components and networks required for the battle." The final word goes to Diane Green, founder of VMware and now running Google's enterprise operation. This is really early. So there is still plenty to happen and the potential is huge.